Hey everyone, welcome to Control System Lectures. Today we are going to analyze the stability using bilinear transformation. So bilinear transformation, the transformation is performed by substituting z equal to 1 plus r by 1 minus r in the characteristic equation of the system. Suppose your characteristic equation in z plane is this one, a n z raised to n plus a n minus 1 z raised to n minus 1 plus a n minus 2 z raised to n minus 2 plus etc. up to a0 equal to 0. Okay, so you here a n is greater than 0. And using bilinear transformation means you have to substitute z as 1 plus r by 1 minus r. So you substitute z as 1 plus r by 1 minus r. So substitute for z in this equation. So you will get a n into 1 plus r by 1 minus r raised to n plus a n minus 1 1 plus r by 1 minus r raised to n minus 1 plus etc. up to a0 equal to 0. Next you simplify this equation. Okay, if you simplify this equation you will get a new characteristic equation bn r raised to n plus bn minus 1 r raised to n minus 1 plus etc. up to b0 equal to 0. So how to check whether the system is stable? So a system is stable if both the necessary and sufficient condition for stability are satisfied. So what is the necessary condition and what is the sufficient condition? So in this method, the necessary condition for stability is that the coefficient of this equation 3.89 should be positive. So that is the necessary condition. Sufficient condition for stability is that there should not be any sign changes. There should not be any sign change in the elements of first column of root array. You have to form the root array. I will explain that later. So in that root array, there should not be any sign change in the elements of first column of root array. If these two conditions are satisfied, the system is stable. Okay, we will discuss one problem. So this is the problem. Given that a new equation is given, f of z, this is your question, f of z is equal to zq plus zq minus 0.2 z square minus 0.25 z plus 0.05 equal to 0. So first step is transformation, z equal to 1 plus r by 1 minus r. You simply substitute z as 1 plus r by 1 minus r. So you will get z becomes in terms of r, so you can write f of r. So f of r equal to 1 plus r by 1 minus r the whole cube minus 0.2 into 1 plus r by 1 minus r the whole square minus 0.25 into 1 plus r by 1 minus r plus 0.05 equal to 0. So next step is you have to simplify this equation. So here you can write that. You can see that the denominator term is 1 minus r the whole cube. Here 1 minus r the whole square. Here 1 minus r. So on multiplying throughout by 1 minus r the whole cube, we get here 1 minus r the whole cube and 1 minus r the whole cube cancel. So you will get 1 plus r the whole cube minus 0.2 into 1 plus r the whole square into here 1 minus r the whole square and 1 minus r the whole cube. So you will get 1 minus r minus 0.25 into 1 plus r into 1 minus r here in numerator 1 minus r the whole cube. If you cancelled in numerator you will get 1 minus r the whole square plus 0.05 into 1 minus r the whole cube equal to 0. And you open the bracket. So you will get, here you can write this as 1 plus r into 1 plus r the whole square. 1 plus r the whole square means a plus b the whole square means a square plus b square plus 2ab. Like that 1 plus r square plus 2r minus 0.2 into 1 plus r into 1 plus r into 1 plus r into 1 minus r. So a plus b into a minus b. So a square minus b square. So 1 minus r the whole square minus 0.25 into 1 minus r into 1 minus r the whole square plus 0.05 into 1 minus r into 1 minus r the whole square equal to 0. Again, you open the bracket and you simplify this equation. So finally, you will get 0.9 r cube plus 3.6 r square plus 2.9 r plus 0.6 equal to 0. Okay, so this is the new characteristic equation in R. So how to check whether the system is stable? So for checking whether the system is stable, first condition is you have to check the coefficient of new characteristic equation. So here you can see that all the coefficient like that 0.9, 3.6, 2.9, 0.6, all coefficients are positive. So this is hence the necessary condition for stability is satisfied. If all coefficients are positive, the necessary condition for stability is satisfied. Next, for sufficient condition, you have to construct the root array. For root array, you can see that the highest degree is r cube. So the first column will be, you have to write your terms, like what are the terms? R cube term, then next is r square term, r term, r raised to 0. So these are the terms: r cube, r square, r raised to 1, r raised to 0. And next you have to form row 1. Row 1 means you have to start from r cube. So you have to start from r cube 0.9. First element will be 0.9. Next you have to take next odd term, that means 2.9. So 2.9. Okay, so you have to start from 0.9, then r cube term, next odd term, that means r square means it's an even term, so you don't take that. Next alternate term is r raised to 1, that is an odd term, so you have to write that. So 0.9, 2.9, that will be your row 1. Next you start from r square, so 3.6, that is the first term. Then next even term r raised to 0, that is 0.6. So 3.6, 0.6. Okay, just write the alternate term. First 0.9, 2.9, next 3.6, 0.6. So you got 2 rows. So next row, how you will write? For writing next row, you have to take this procedure. So the value will be, this value will be, how you will get? 3.6 into 2.9 minus 0.9 into 0.6 divided by 3.6. That will be 2.75. Okay, so this is the procedure for writing the elements in root array. Okay, so 3.6 into 2.9 minus 0.9 into 0.6 divided by 3.6. That will be 2.75. So you got this row. So last row, how you will get? You take these 2 rows. Okay, so you will get 2.75 into 0.6 minus 0 into 3.6 divided by 2.75. So that will be 0.6. Okay, in this way you can find out all the terms. Okay, for finding the term you have to take 2 rows above that element. Okay, so here next you have to check the elements of first column in the root array. So here you can see that there is no sign changes. All the elements in the first column of root array are positive. So sufficient condition for stability is satisfied. There is no sign change in the first column of root array. So here you can see that the necessary and sufficient condition for stability is satisfied. So system is stable. Okay, I hope you understand this. Thank you.